Thanks for noticing that. That's perfectly fine. All right, well, let's continue on our discussion that we just briefly started on Monday. And what we're looking at is connecting different spaces to different aspects of a matrix. So right at the end of class last time, we defined what we meant by the row space of a matrix. Row space is just the span of the row vectors. So treating each row like it's a vector.
Thank you.
You're welcome. Treating each row like it's a vector, doing the set of all linear combinations of those row vectors. That gives us a space, which we refer to as the row space. Since each of the rows would have n components in them, that space is going to be a subset of Rn, a subspace of Rn. Likewise, if we treat all the columns like they're vectors and look at all the span of the columns, the set of all linear combinations of the columns, that gives us what we refer to as the column space of A. Since each of those would have m components going down the rows, that's going to be a subspace of Rm. Null space is something we already computed, but we're just giving it a different definition. Null space is the solutions to the associated homogeneous system of the matrix. So the solutions to the equation AX equals 0. Since to make that multiplication defined, I need X to be an n by 1 vector. So that's going to be a subspace of Rn as well. So the row space and the null space are subspaces of Rn. The column space is a subspace of Rm. All right, just to keep those straight. We didn't write down what the notation was for each of these last time, so let's do that now. For your row space, we would denote it as ROW of A. Big surprise. For column space, you would use COL of A. And for null space, you'll use null of A. So those are just the notations for those particular spaces. All right, so let's do the next definitions here. The next one we have is the rank of A. The rank is basically, if you put this matrix in reduced row echelon form, you can count the pivots in there, right? So the rank, by definition, is the number of pivots in the reduced row echelon form of A. But it has some significance to go along with other aspects of the matrix. So let's say you were interested in figuring out a basis for a subspace that we had. So when we did the basis idea, we went through, we took the vectors, put them in as columns, looked for where the pivots were, and went back to the original matrix and picked out the columns that had the pivots, right? You agree with that? Okay. So notice that the pivots there are going to correspond to each of the vectors that are going to be in your basis for the column space, because I just made a matrix and put those in as columns, right? You agree with that? So that's going to get the number of pivots are going to give you the number of elements in the basis. In this case, it'll be the number of elements of the basis in the column space. Well, when we talk about number of elements in a basis, what quantity do we say we were computing when we counted number of elements in a basis? What do we also call that for the vector space? Dimension, right? So the rank of the matrix is also going to be your dimension of your column space. Oops. So writing it, rank of A is just what we use for the notation for rank. That's going to be the dimension of your column space of A. those two things will be the same. But we can also think about it in terms of rows. If we do the reduced row echelon form and look at the pivots, notice that when you're doing row operations, and we're going to talk about this here in a second, when we're doing row operations, pardon me, goodness. When we're doing row operations, that is linear combinations of the rows, right? That's what we're doing, right? Because we take, either we move them around, but that's not very interesting, but we'll do a constant times one row and add it to another, right? So basically we're just changing out things with linear combinations. So when we do row operations on the matrix, we're not changing the row space at all, because we're just combining rows as linear combinations of them, right? So when we get to the end, for what we could use for a basis for your row space are just the rows that are left. Because those are the non-zero rows that would be left. They're going to be linearly independent by the way the pivots match up. Well, we're going to see that here in a minute. Okay, so we're going to do more than just say it out loud. But we can talk about how those, all we're doing is just doing linear combinations of the rows. What we end up with will be a basis. And that's going to be the same as the number of pivots, again. So not only is the rank equal to the dimension of the column space, it's also equal to the dimension of the row space. So again, we're going to do examples of this, so I'm going to do more than just say it. But when you want to find the basis for the column space, you're going to take the matrix, row reduce it, look where you have pivots, and go back and get the corresponding columns. When you want to find the basis for the row space, you're going to row reduce it, and you're going to use the rows that are in the reduced row echelon form as your basis. Okay? So it's a little bit different process, but notice it's still going to be the same number in each of them because those are going to be the ones that have the pivots left over. Okay. So even though the row space and the column space potentially are in different R whatevers, right? The column space is a subspace of Rm, the row space is a subspace of Rn. So even though they might be in different spaces, they're going to have the same dimensions. Doesn't matter whether necessarily where they live, they will have the same number of elements in a basis. They'll be the same size of ideas. All right. Well, if the rank is referring to, or at least is equal to, the dimension of the column and the dimension of the row space, what do you think the nullity is going to refer to? This refers to the dimension of the column, the dimension of the row. The nullity is going to refer to, what do you think? The dimension of the null space. Yeah, exactly. So there's not any fancy notation for nullity. It's literally nullity of A. This is going to be the dimension of your null space of A. And that is the definition. The nullity is the dimension of the null space. So far, so good? Okay. Like I said, we're going to do this as an example. But why are we talking about all of this? All right, so the first thing is that we're going to talk about why we care about column space and null space. So this first part here is actually a little bit about why we care about column space. When we do null space, we're talking about finding the set of solutions to AX equals 0, because we're looking at the associated homogeneous system. We know that's always consistent, right? Because what's always a solution to any homogeneous system? Zero vector, right? We can always use the zero vector. We might have more, but we always can use all zeros for the x, and that will solve the homogeneous system, right? Okay, so no matter what. But if I have something where I change it to a non-homogeneous system, we may or may not be consistent, right? Okay. So think about what would happen if we're doing if we're just solving something, right? If we say if I want to solve this, we think about putting it in a matrix, right? So you would have whatever your column 1 is here, whatever your column 2 is here, and so on down the line, whatever column n is here, right? You agree with that? Okay. Let me write it as augmented. I put a bracket. And then your B would go here, correct? What's going to happen if this is inconsistent? If you put this in reduced row echelon form, what are you going to see at some point if it's inconsistent? We're going to see a row of zeros where? Okay, so it'll be, but what, if it's going to be inconsistent, what do I also need? If I have all zeros, does that tell me it's inconsistent if I go all the way across? All the way this way? No. Okay, what do I need? Yeah, it'll be all zeros here, and then I'm going to see a 1 here. There's going to be a pivot in that last column, right? There might be rows of zeros all the way across below it, but somewhere along the line, if you put this in reduced row echelon form, you're going to see zeros to here, and then a 1 here, right? That's what's going to look like when it's inconsistent. We agree? Okay. Notice that if you do your reduced row echelon form, you should also see some pivots over there. Hopefully, well, there are probably some pivots over there, correct? What happened to the rank of the original matrix when we augmented it by the constant vector? Did it stay the same or did it go up? So this would, remember, rank is what again? Number of pivots in the reduced echelon form, right? If I ignore this column, I'd have the rank of the original matrix, right? Did the rank of the augmented matrix go up or did it stay the same? If it's inconsistent. It went up by 1, right? Because I got a pivot in that constant column, didn't I? Okay. So we notice that if it's going to be, this is one of the things that we can talk about. If it's inconsistent, the rank of the augmented matrix is the rank of the original matrix plus 1. It goes up by 1, right? We end up with a pivot in that final column. So if it's going to be consistent, we better keep the rank the same, right? If it's going to be consistent, if I have a row of zeros at the bottom, there better be a 0 corresponding in the constant column, correct? We've talked about that before, haven't we? Right? If it's going to be consistent, if I see a row of zeros, it better be a row of zeros all the way across. Agreed? Okay. So if it's consistent, the rank of A augmented with the B is going to be the same as the rank of A. It didn't change. So if it's going to be consistent, the rank stays the same when I augment. Now, how does this tie to column space? Let's ignore the fact that I augmented. Okay? Let's just say I put a set of vectors in a matrix and I row reduce. And I wanted to figure out a basis. That's what we do, right? If we want to figure out a basis from a set of for a span of a set of vectors, we stick them in columns and row reduce, and then what do we do? Yeah, so exactly. You go back and look at the columns that have the pivots, and you pick those out for your vectors and your basis, right? That's what we do, correct? If I augment and the rank doesn't go up, if I stick this extra vector on the end, not worrying about the augmented part, it's the solution set. Just I stick an extra vector on the end, and I don't get a pivot. Am I going to include that column in my basis? No. We go back to the original matrix and pick out the ones that have pivots in them, right? Right? So again, if I stick this vector on here and I augment this, if I stick this vector on here and I row reduce, and I don't see a pivot, then I'm not going to include that in the basis. I don't need it, because why? what does that mean for that particular column? Why do we throw them out? What's the whole point of throwing out the other columns? Yeah, they're dependent, right? I can already write them as a linear combination of the other columns, right? That's the whole reason why we throw them out. We don't need them because they already depend on previous columns, right? So if I can throw this one out, then that means I can already write it as a linear combination of the other columns, right? Or, said another way, this is already in the span of the column space. It's already in the column space. It's already in the span of the column vectors, okay? So let's tie these two ideas together. If my rank doesn't go up, if I'm in this scenario, this tells me that your B is already in the column space of A. That's what that tells us. And if it's in the column space, then it's going to be consistent. It works both ways. Because if it's already in the column space, then I know when I row reduce, I'm not going to get a pivot in that final column. So this is one of the things that we care about with the column space, is that we can actually have an if and only if statement. We can say that this system is consistent if and only if. By the way, if a mathematician writes if two ifs, it means if and only if. We're lazy. So if if and only if our vector is in the column space. So this gives us one reason why we care about column space. All right, so if the system is consistent, that means that I can write the vector that I'm interested in as a linear combination of the columns. All right. So then if it is consistent, then what form does the solutions take? And that's what's on the next page here. And again, if you've seen differential equations, or if you're currently in differential equations, you talk about solving non-homogeneous differential equations. So let's look at the example first, and then talk about the theorem, do the proof of the theorem. So here is a first order differential equation. First order because it involves the first derivative. You can check easily that one solution to that differential equation is x e to the x. Take its derivative, plug it in, and you'll see that you get e to the x with the gun. Okay. That's a Calc 1 problem, so I'm not going to go through it now. Okay. All right. But you can check that that is a solution. And then if I replace this with a 0, well, we've already talked about what function is its own derivative, right, before? E to the x works, and then constant times e to the x works. So the associated homogeneous system has solution a constant times e to the x. If I pair those two pieces together, then I can write every single solution to that differential equation as one particular solution. That's what they'll use for the sub p part. One particular solution plus the general solution to the homogeneous system. That's why there's a sub h part. That's the consequence of what this theorem says. And this is exactly how you solve these things in differential equations. You find the solution to the homogeneous system, and then you go look for a solution to the non-homogeneous equation. I should say equation. Differential equations is looking at an equation. This particular theorem from linear algebra allows us to do that in differential equations, for example. So what does the theorem say? It says that I can write every single solution to a consistent non-homogeneous system as use that one particular solution and then add on some other homogeneous part. Okay? This allows us to do that. Okay? We know that, pardon me. homogeneous systems, if they have non-trivial solutions, give you infinitely many. We're just saying that we can always write every single solution this way. So if the AX equals B has infinitely many solutions, I can generate all of them by looking at one specific one and then the associated homogeneous solution, the general solution to that. I don't have to look for a general solution to the whole thing every single time. And that's exactly what we're doing with differential equations. Okay. All right. So let's see how the theorem works. It's actually not bad. Okay. All right. So let's let, I'll call it x sub p be a solution to the system. Right? So I want to talk about generating every solution, right? That's the idea here, correct? Okay. So notice that the thing that I'm trying to go for is whatever the y is. So now let's let our y be another solution. Doesn't matter what it is, just pick some other solution. What if I take A and multiply it by y minus xp? What do I get? xp is a solution to ax equals b. Y is also a solution to be ax equals b. What do we end up with if I take a times that? A 0, right? Because I can distribute the a through. Oops. Each of those is a solution to ax equals b. So a times y has to give me b. A times x sub p has to give me b. So each of those is 0. Or sorry, each of those is b. Subtracting gives me 0. I said that wrong. Okay. So what can I say that this particular vector is a solution of? A homogeneous, right? This is a solution to the homogeneous system, isn't it? So now let's let, if I can spell, now let your x sub h just be the difference between these two things. Then the x sub h is a solution of the associated homogeneous system, and clearly, hopefully it's clear, that the y is equal to xp plus xh. Again, the whole premise of this is that when you solve systems of linear equations or differential equations or wherever else linear algebra might be applied, when you're solving these things, if you don't get one solution, you know it's consistent and you don't get exactly one, then you get infinitely many, right? If it's not one and there is a solution, then there's infinitely many solutions, right? So the idea here is, what do the infinitely many solutions have to look like? Turns out it's a lot easier to solve homogeneous systems or homogeneous equations in general than it is to solve non-homogeneous equations. Okay? Just as a general rule, it's a lot easier to solve those kinds of things. Okay? I can give you another differential equation example that shows what I mean here. Anyway, pardon me. So if I can solve the homogeneous system and get a general solution for that and find the infinitely many solutions here, then to find the general solution for the non-homogeneous just involves finding a particular solution, just one. I don't have to find all of them for the non-homogeneous. I already took care of the infinite part here. Then I just have to go look for one here, which is a lot simpler idea to look for one than look for infinitely many. Okay? So generally speaking, it's easier to solve a homogeneous system to get the infinitely many solutions, and then just find a particular solution than it is to try to find all the infinite solutions to the non-homogeneous systems all at the same time. So we're breaking into pieces because it's easier to find that homogeneous system first, solution first. Okay. Let me give you an example of what I mean by that from a differential equation standpoint. Say we had this non-homogeneous equation. So this is what we refer to as a second order linear differential equation. Second order because it involves a second derivative. That's the highest order derivative I have. Linear because any pieces that have a y in it are just y's, right? I'm not squaring the y. I'm not multiplying the y's together. I'm not putting y inside of a function. Okay? If it's a linear differential equation, then linear algebra techniques apply. Okay? So I can look at the associated homogeneous solution. I look at the associated homogeneous equation first, look at that particular differential equation, and then I look at that and say, I need a function that when I differentiate it once and differentiate it twice, and then combine those things, I get 0. What type of function do you know satisfies that kind of idea? E to the x, e to the some constant times x, right? So what we do is we assume your y looks like e to the rx, right? Because that's a function that we know when we differentiate it, a copy of that function comes back out again, right? We agree? Yeah. If I take the second derivative, I would get r squared e to the rx. Take the first derivative, you get r e to the rx. I get that. What can I factor out of every single term? E to the rx. That product now has to be 0, and it has to be what we refer to as identically 0, right? It has to work. It has to be 0 no matter what I plug in for x. Is e to the x ever 0? No. So the only part that is 0 is the r squared minus r minus 6 is 0. Factors. So your r has to be 3 or negative 2. So it gives you a couple of ideas. So I know that e to the 3x would work, e to the minus 2x would work and give me 0. And if you do any linear combination of those two things, you also get 0. So it turns out here that your homogeneous solution looks like a constant times e to the 3x and then some other constant times e to the negative 2x. Now, there's a little bit more theory in there that I'm not going through because I'll save it for a differential equations class. Since it's a second order equation, I know that there's 2 linearly independent solutions that work. And these are not constant multiples of each other. So they're linearly independent, so I know every solution has to look like that. Like I said, there's a little bit of more theory that's not involved in this class, okay? But notice how straightforward that was to find the homogeneous solution, right? What did I change it into? Changed it into an algebra problem. Oh, shocking, I'm in algebra class. Okay. It changed into an algebra problem, right? That was a lot easier to solve. Now that I have the homogeneous solution, I just need to go back to the original and say, okay, now how do I find one solution to that? And I can write the general solution. And then there are some differential equation technique tricks and techniques to use to figure out what you're going to do for the general, the particular solution that you need. In fact, since I know e to the 3x is in my homogeneous system, our homogeneous solution, I wouldn't use e to the 3x, but I need an e to the 3x when I'm done. So you would start with something that looks like an x times e to the 3x and get everything to work out that way and make your constants match. So you would assume that your particular solution has the form something times x e to the 3x, and then you figure out what the something is. It's not too bad. Shockingly enough, you'll end up with an equation that you have to solve. A literal equation you have to solve. You do some more algebra, but that's the idea. Okay. But again, I'm not going to go through the particular part. I'll save that for a differential equations class, because you're looking at what the form of the function has to look like and what its derivatives look like. But from the homogeneous standpoint, this was straightforward, right? Literally just solved an algebra problem to get here. This is the infinite part that you're going to worry about. So then to figure out the non-homogeneous system, you just have to go find one. And that was what the point of that previous theorem was. Okay? So even with not having differential equations, we did this quickly. I waved my hands out of it a little bit, but we did this quickly, right? Right? That's the whole idea, and that's the whole idea of the theorem. Questions on that at all? This kind of stuff, you can tell I enjoy this kind of stuff, perhaps. All right. All right, so let's look at our next example here. Here is a system of equations, and what I'm going to illustrate here is how to write this as your particular solution and then plus the general solution to the homogeneous system. Okay? We've already done this, we just haven't done it in this language before. What would you do to solve this system? Well, you create your augmented matrix and you row reduce, right? Okay. So I don't have the augmented line in here, so let me draw it in here real quick. So this is where we would augment this part here, augment that part there, right? Is this system consistent? Yeah, because I don't have an inconsistency in the bottom row, right? So I'm good for that, correct? Where are your what columns are your free variables? 5 and 6, right? So x2 is free, x5 is free, x6 is free, right? So we can write, say your x2 is R, your x5 is S, your x6 is T, right? So if I solve for x1, you would get -1 minus 3r minus s plus 2t, right? If I plug those r, s, and t in and move them over, right? Your x3 would be what? -5 plus s minus t, and I didn't leave myself a lot of room here. Your x4 would be -2 minus 4s minus 2t. Everybody see where those are coming from? I know I did it quickly, but we've done this before, right? Now, if we rewrite this, and we've done this as well, this is exactly what we've done before. I'm just illustrating the point that we talked about. Notice you can pull your constants off and then break it up as r times -3, 1, 0, 0, 0, 0. Your s times -1, 0, 1, -4, 1, 0. And your t times 2, 0, -1, -2, 0, 1. Right? This is the part that doesn't have any variables associated with it. These are your coefficients on the r all the way down. These are the coefficients on your s all the way down. These are your coefficients on the t all the way down. I know I went through that quickly, but we've done this before, right? That's why I went through it quickly. But notice, this has the exact same form that we just talked about. This right here would be your solution to the particular solution to the non-homogeneous system. If you plug in -1, 0, -5, -2 into the system, it should solve it. Or sorry, yeah, well, -1, 0, -5, -2, 0, 0. You should get ones for every single equation. That should solve that particular system. The rest of this, all of this, is your solution to the associated homogeneous system. So if you plug in any linear combination of those three vectors, you'll get 0 for every single equation. We've done this, we just haven't said we've written it in this form, right? But again, that's the whole point of the theorem. I can write every solution to the system as a solution to the system plus the general solution to the homogeneous system. And that was why we broke it apart like that way back when we were doing systems and linear equations. Okay? Questions on that at all? Stunned by the linear algebra here? All right. So that's the idea. And again, it doesn't just apply to systems and linear equations. It applies to, like I said, things like differential equations. And there's all sorts of other function spaces that it applies to. All right. Let's see if we can go back up to here. And let's do the exact same matrix. We haven't changed anything. But let's not worry about it being augmented. Let's just say that this is my matrix to start with. Okay? I'm not treating this as the matrix that we just had from the previous example. I'm just treating it as a matrix. Okay? Right? So ignore the fact that we had a system of linear equations to start with. Okay? So this is your matrix that we're going to start with. All right? We've already asked this about before. What effects do elementary row operations have on either the row space or the null space? Well, elementary row operations are linear combinations of rows, right? So does that have any effect on the row space at all if all you're doing is just playing around with linear combinations of the rows? No. So elementary row operations have absolutely no effect on the row space. Does it have any effect on the null space? Well, isn't that exactly how we find the null space? Is that you solve the associated homogeneous system, right? You would do row reduction and then write down the solution. So elementary row operations have no effect on the null space either, okay? So none is the answer to this question. They have no effect at all. It doesn't change it. Okay? Right? No effect at all whatsoever. Okay? So we already know how to find bases for these by the stuff that we've already done. Okay? Pardon me. All right. So if I'm looking for a basis for the row space, here's the reduced row echelon form. We already did that before, but here's the reduced row echelon form. When you want to pick out a basis for the row space, you just pick out the rows that are left. That is a basis for the row space. That's it. Okay? So basis for the row space here would be 1, 3, 0, 0, 1, -2, -1, 0, 0, 1, 0, -1, 1, -5, and 0, 0, 0, 1, 4, 2, -2. That's it. That's all you have to do. Start with your matrix, row reduce it. The rows that are left form your basis. That's it. Because again, elementary row operations don't change the row space at all. All you're doing are linear combinations, pardon me, of your rows to get from one to the other. So what that means for us in particular is that if you think about working backwards, if I started with this, do all your row operations in reverse, you'll end up back over there, won't you? Right? So I can write every one of these rows in terms of those three, is what that says. So that's all the three that I need. Okay. For your basis for your null space, well, I have to solve the system, right? So again, I said we're going to treat this like it's a new matrix, correct? So again, if I think about this being times some x and equaling the zero vector, I have to find a basis for that space. To find a basis for that space, I need to look at the columns without pivots, right? Right, that's what we have to look at for those. Okay. So again, your x2, this would be your second column, your fifth, your sixth, and your seventh don't have pivots, right? Okay. So if I want to, pardon me, if you want a basis for this, then let's just write out the solutions to start. That was weird. Write out the solutions to start with here. Your x1 would be, I need what? Basically a q, r, s, and t. So a negative 3q minus r plus 2s plus t. Your x2 would be q. Your x3 would be what? R minus s plus 5t. Your x4 would be negative 4r minus 2s plus 2t. And then your 5, 6, and 7 were all free. So that's your r, s, and t. Agree with that? Remember, you said basically have to move, all the signs flip when you move them across the equation, right? Or across the equal sign, I mean. So, what is your r multiplied by? What vector is your r multiplied by? What are your coefficients for your r reading down? Good. All right, those are your coefficients for your r going down. So that's one vector that would be in your null space. What are your coefficients for your s? Well, I guess I needed my q too, didn't I? I forgot my q. We did the r. I need one more. Sorry. Let me do that one first. What are your coefficients on your q? It's just negative 3, 1, and a bunch of zeros, isn't it? Sorry about that. There are 5 zeros in there. Squeezed it in. For your s, you'd have 2, 0, negative 1, negative 2, 0, 1, 0. And your last one, I don't know why I got so much phlegm today. 1, 0, 5, 2, 0, 0, oops, 1. So again, the first one is just reading off the coefficients of the q as I'm reading down. The second one is the r. The third one is the s. The fourth one is the t. Ordinarily, we were writing those as columns, right? We wrote out the solution. So we just did in the previous example, isn't it? Goodness. Again, this is how we find the basis for your the null space. We look at the associated homogeneous system and solve. All right, so we said that the elementary row operations don't affect the null space and don't affect the row space. Right? However, elementary row operations do change column vectors, correct? In particular, notice that in your reduced row echelon form, I have a row of zeros in the bottom, correct? If I were to do linear combinations of your columns for this matrix, the only thing I can get out in the last component is a 0, isn't it? Notice over here I can get all sorts of things that aren't zeros, right? So we don't find a basis in the column, we don't find a basis from the column space by looking at the reduced row echelon form. We go back and look at the pivots and then pick out the corresponding columns that go with those pivots, right? So when we do our basis for our column space, we want columns 1, 3, and 4, correct? So we would have 3, -9, 2, 6, 2, 4, -1, -1, and -7, -6, 1, -1. But notice again here, like I mentioned at the beginning, what's the dimension for your row space of A? 3. I can see the 3 vectors in there, right? What's the dimension for your column space? Also 3, isn't it? For your column space. These two have, even though they're in different spaces, right? These vectors live in R7. These vectors live in R4. Even though they live in different spaces, there's the same number of them. So the column space and the row space, from a dimension standpoint, have the same size, even though they're living in different spaces. And again, our rank for our matrix up there would also be 3. All right. So again, elementary row operations do affect your column space. They don't affect your row or your null space. But we still use the reduced row echelon form to help us figure out the different bases that we need. All right. We'll finish this stuff up next time. I think we got a couple more pages. Notice that one of the things we'll talk about is the return of our mega theorem. We're talking about the mega theorem. So make sure you find your page that you've got all those equivalent properties. We're going to add several to it on Friday. All right. Have a good one. We'll see you then.